Okay, so I want to review some hints and answers to the problems in this 1.2b problem set. And what I'm going to do here is offer you answers, but not necessarily explanations, because I want you to fill in those explanations in your groups. But hopefully this will offer a little bit of affirmation that you are on the right track. I can't help but point out this lovely diagram of a cyclic group, the Cayley diagram of a cyclic group, and the diagonals here. When I've been working with some students in office hours, they are sometimes surprised that I can construct the Cayley diagram of a cyclic group so quickly. And all I have to keep in mind is these diagonals. Okay, so just remember that. Okay, so for question one, we have to determine which of these form groups. So the first one is not a group. The second one is a group. The third one is a group. The fourth one is a group. On the second line, the first one is a group. The second one is not a group. The third one is not a group. And the fourth one is a group. Now, the third one might surprise you here that it is not a group. And for that one, you have to remember what the action is in C4. What operation is this 0, 1 subgroup taking? Okay. Or sorry, it's not actually a subgroup, so subset. So what action is the 0, 1 subset taking? Okay, so for question number 2, you should do this in a proof by contradiction, probably, or let me think. Prove that A is equal to A inverse. Is there another way? I think that I would do like a contradiction. So you could do it like, for example, saying that the order of A is greater than the order of A inverse, the order of A is less than the order of A inverse, and then you get a contradiction both ways. That's where my mind goes immediately, but I'm sure that there are many, many ways to do that problem. The third one, showing that if A has infinite order, then you can never stumble upon two orders being the same. So assume that they are and show that A does not have infinite order. Okay. If G is a group and A to the power of 6 is equal to E, then the order of A could be 1, 2, 3, or 6. Your answer should tell us why. Those are the only possibilities. In question number 5, why N, Z are subgroups of Z, you could use one of the subgroup tests, or you could prove all the properties of a subgroup. Showing that the set of odd integers does not form a subgroup, you cannot use a subgroup test. So make sure that you are not using a subgroup test, because a failure of a subgroup test does not show that something is not a subgroup. Instead, you need to show that the odd integers lacks one of the properties of a subgroup. In particular, I would think identity is what you want to go to here. And then number C is kind of a speculative question. Hopefully your answer is no. The proof of this is a little bit difficult, but you should probably be able to approach that proof by now. Maybe not when you first got this question, but by this point in the course, you should be able to. In question number 6, H and K are subgroups of G. Is the intersection a subgroup of G? Your answer should be yes. It is a subgroup. and you could use one of your subgroup tests to show that. Is the union a subgroup? The answer should be no. And you cannot use a subgroup test because a subgroup test, again, only shows that something is a subgroup. It does not show that something is not a subgroup if it fails. So to show that the union is not a subgroup, you would want to show, for example, a counterexample. So a case where you had two subgroups of G whose union was not a subgroup G. In question number 7, showing that Z is equal to the intersection. I heard that some people kind of said it was just obvious, but you need to break this down as group theorists, as mathematicians. You need to break the explanation down. And a great way to show that two sets are equal is to show inclusion in both directions. So you want to show that ZG, the center, is contained in this intersection, and you want to show that the intersection is contained in Z of G. In question number 8, we want to prove that these two sets are equal. The normalizer is equal to the centralizer in the case where H has order 2. And again, the best way to do this is to do an inclusion in both directions. So to show that N is contained in C and to show that C is contained in N. And then if you show that, then you will show that they actually have to be equal to each other. Once you simplify each of these in the case, especially if you simplify the normalizer, in the case where H is a subgroup of order 2, this statement becomes pretty intuitive. So I would suggest first break it down. First, think about what NG of H has to look like if H is order 2. And then secondly, show your inclusions in both directions. In question number 9, let A and B be elements of a group G. And if the orders of A and B are relatively prime, you want to show that the intersection of the subgroups that they generate is just E. So the best way to show this is to assume that you have something in the intersection and then show that that implies that the element is E. And of course, since you have something about, something about the orders of these elements, examine the order of that element that is in the intersection. In question number 10, we have A and B are group elements that commute with each other, and we know now that the intersection of the subgroups that they generate is equal to E, and we want to show that the group contains an element of order LCM of M and N. We also know by the last sentence that it's important that A and B commute with each other. So how can we possibly approach this? Well, you should explicitly construct an element that has this order. So write down a representation for an element of this order. Now, you don't have very many options because you don't know a lot about the groups, so that's a big hint. Write down an element of this order, and then for the counterexample, explicitly show a group where you have A and B not commuting, and then maybe show that you do not have an element of order LCM in the entire group, LCM of M and N in the entire group. Okay, that counterexample, again, should be a little bit more approachable now that you have more examples at your fingertips. You can also use Group Explorer to try to help generate those. Okay, so I hope that this has been helpful and that you know that you're on the right track. If for any of these you have every point that I have said and you don't have anything else, you should add more to your explanation, because I'm just giving you a little hint or a little taste. You should have a lot more in your explanation.